Okay, so we finished up the last topic with a bit of a look at the four fundamental interactions or forces in our universe, right? Including a look at their relative strength and the distances they act over and the types of particles they act on. Want to come back to the strength now, okay? Because the strength of these forces has been kind of a limiting factor in how well we've been able to probe matter, look at what's in there, get to know the structure of things, right? What is stuff made of? Because to separate bound particles, you have to overcome forces. To overcome forces, you need energy, right? So to separate a book from the earth, a book could be considered bound to the earth by gravity, right? To do that, you have to overcome the gravitational force. How do you do that? You got to give it potential energy, right? And that's not free. It's got to come from you. It's got to come from the breakfast you had that morning, the chemical energy in there, right? You need energy to overcome that force. To ionize a hydrogen atom, to break the electron from the proton, you need to overcome the electrostatic force. That electron is attracted to the proton. How do you do that? You need energy. 13.6 electron volts, you'll recall from chapter 16. To break apart a nucleus, as we have seen, you now need to overcome the strong force, okay, between the nucleons within the nucleus. Again, you need energy. And that leads me into the next one here. You need a lot of energy, right? What is the strongest force as long as you're within the nucleus? By far the strong force, right? Strong force is the strongest force. It's just that once you go outside of the nucleus, the effects of the strong force drop off to zero. So to beat the strongest force, you're going to need the most energy, right? So we've witnessed the huge amounts of energy that can be associated with the strong force, right? Remember fission and fusion? Incredible amounts of energy involved here with the strong force. And this was our issue. We couldn't really get those kinds of energy until we could, okay? So if we accelerate particles to very, very high energies with huge voltages, I'm talking huge voltages, okay? And, well, some very clever engineering to suspend them in magnetic fields and keep them on track and everything, we can get high enough energies to overcome even the strong nuclear force. The math involved is pretty basic. It's at a surface level, it's your physics 20 stuff. We're trying to overcome a force across some distance, right? You can think of that as a separation distance of nucleons if we're doing the strong force. Yes, there's a little calculus involved in this because the force is not constant, but the idea is basically the same. Okay, force times distance, that's work, which is energy. Whoops, change in energy, right? Which is Q times V. A big voltage will give you a lot of energy if you let it go long enough. The idea is overcoming a big force requires a big voltage. We couldn't get that big of voltages for a while until our engineering and our technology had advanced, right? This is the thing. Science feeds technology, which feeds science, which feeds technology. They're in a mutualist relationship. Sometimes our technology leads to new science, and then that science can lead to new technology, which in turn leads to new science. Now, one of the breakthrough technologies that we've had in the last half century in physics, particle physics especially, is, well, particle accelerators. The most famous one being the Large Hadron Collider. You might have heard of it, but there are many all over the world. It's huge. It says it's in Switzerland, but it actually goes into France as well. It's pretty big. When you see it from above, it's just a big circle. It's something called a cyclotron. It essentially uses magnetic fields and very high voltages to accelerate particles up to very high energies. Okay, in the tera electron volt range. Recall, it takes only 13.6 electron volts to ionize hydrogen. Rutherford's gold foil experiment, where you had to have a positive alpha particle collide with a positive nucleus, right? Which is certainly overcoming the electrostatic force. That's a lot of energy needed to do that. That took about 10 mega electron volts, which is a lot, but now we're talking about tera electron volts. That's two prefixes beyond mega, right? It goes mega, giga, tera. So giga is 1,000 times bigger. Tera is 1,000 times bigger. So we're talking 1,000,000 times bigger than a mega electron volt when we're talking about tera electron volts. We're dealing with a lot of energy here. In other words, development of things like particle accelerators, we were finally able to smash stuff we couldn't smash hard enough before. We can smash stuff together and see what comes out. We also, truthfully, even before we had particle accelerators, we were using more simple, compared to particle accelerators, technologies like cloud and bubble chambers. And we were able to study even higher energy particles from cosmic rays, okay? Cosmic rays are charged particles, they're mostly protons, that come from outer space. Not entirely sure where all of them come from. We have some pretty good guesses about where some of them probably come from supernovae very far off, or quasars or active galactic nuclei, right? Either way, stupidly high energies. We're talking up to 10 to the 14 mega electron volts. There's one famous cosmic ray particle that's actually called the oh my god particle, because when physicists recorded it, they all said, oh my god. If their readings were accurate, it had an energy of 10 to the 20 mega electron volts. That's about 50 joules. We're talking about a subatomic particle that had the same energy as a baseball going 90 kilometers per hour. Take a second to imagine that, right? This thing was going incredibly fast. Okay, anyway, the point is these cosmic rays and these high energy particles in particle accelerators, when they collide, we can overcome the very strong forces that are binding things, and that allows us to probe it, right? You can't really look at what something's made of unless you can break it apart. And now, examining all these collisions, we started to notice particles we had never seen before. New subatomic particles. They weren't protons, they weren't neutrons, and they weren't electrons. They were smaller than atoms, that's what subatomic means, but they weren't those three things. Okay, so here's actually an image from the Large Hadron Collider. Of course, this is a computer-generated image of a real collision. You can see two particles collided at a very high energy, and some other particles came out of the collision, right? This is what happens when cosmic rays collide with our atmosphere, very high energy particles. And there's it's called a secondary cosmic ray, which is basically a shower of other particles. Some of those symbols you will recognize. You know the neutron, you know photons, you know electrons, you even know positrons. But you don't know pions, you don't know muons, new subatomic particles, and maybe they were even fundamental particles. Maybe they were indivisible. Maybe there were more building blocks than we had originally thought. So why have you probably never heard of them? Why have you never learned about them in any other class? Well, the particles only exist for tiny fractions of a second. I'm talking tiny, like most of them are on the order of about 10 to the negative 20 some seconds. But they do exist. They are real. They are a piece of our universe. Our models of matter would be incomplete without them. Just because they aren't stable doesn't mean they don't exist. So we've been doing it for the last 50 years, smashing stuff together, seeing what comes out, finding particles in cosmic rays, seeing what comes out of those collisions. And we started to tabulate them and keep a list and keep a list. And to date, physicists have confirmed over 300 types of subatomic particles, with many more predicted to exist, to the point where we know, yeah, they're probably there. It's just going to be really hard to actually end up detecting them and measuring them, right? Because that was the case for so many of these. We predicted them with the mathematical models, and then sure enough, once the technology catches up, we were able to measure them and detect them and create them. So our model of matter, once again, gets an order of magnitude more complex, right? So physicists, as they've been documenting, they started to notice patterns and properties, and they started to categorize matter into, well, a few kind of different categories, okay? So you can take all subatomic particles and you can split them up into two main types. There's leptons and there's hadrons. I'll say this at the top, you don't really need to know these classifications of matter in too much depth, but it does kind of help contextualize where we're going to go and the motivation behind where we went. So like I said, leptons and hadrons. What makes a lepton? Well, the big thing is that it does not interact with the strong nuclear force. To this date, there are only 6, well, and they're antiparticles, so 12, that have been observed, predicted, any of that. There's only 6. Now, spin is not something we cover in Physics 30, but hey, what's charge? What's mass? They're just properties, okay? If you are okay with those, you should be okay with the idea of spin. It has to do with their angular momentum that's inherent to them, okay? And it turns out all leptons have a half integer spin, which makes them part of a kind of a different category, fermions. And that just has to do with ways that they interact with each other, again, beyond Physics 30, okay? So key thing is they don't interact using the strong nuclear force, but another defining feature of them is that they are fundamental. They cannot be divided. So leptons are indeed a fundamental particle. They're one of the most basic building blocks. Some examples, the most famous lepton, the electron. Okay, that is a lepton. So one of our original fundamental particles is indeed a fundamental particle. Okay, the electron does actually fit that definition. The neutrino is a lepton. There are actually 3 types of neutrinos. One that is paired to each other lepton. So there's an electron neutrino, a muon neutrino, and a tau neutrino. Again, all beyond Physics 30, but interesting nonetheless. The muon and the tau particles are very unstable. Okay, they're part of what we call the second and third generation of matter because we discovered them second and third after we already knew about the first generation. Okay, but they are basically siblings to the electron. Heavier, less stable siblings. The other main category are the hadrons. Their name means thick. Now, if you're a hadron, you do interact using the strong nuclear force. In other words, the strong nuclear force works on you. And remember those hundreds of subatomic particles we were talking about that started to make the picture look muddy? Most of them fit into hadrons. Hundreds of them have been observed. And the other big thing about them is that hadrons are composite. So they are made of smaller fundamental particles. Now, me telling you that is skipping ahead a bit, okay? That's going to be covered in depth in the next lesson. But just for your understanding of hadrons versus leptons, leptons fundamental, hadrons not fundamental, okay? Like we said, hadrons can then be split up into two categories. We have baryons, which their name means heavy. These things are made of at least 3 quarks, which is part of the reason they have a half integer spin, which makes them also fermions. So you can kind of see that there's 2 systems that we use to classify matter a little bit here. I'll show you that in a sec as well. Lepton versus hadron, as well as fermion versus boson. The other one is a meson. Their name means middle. Middle because they're not as heavy as baryons, but they're not as light as leptons. They are made of 1 quark and 1 antiquark. More on that tomorrow. It's been predicted that you could have more than that. We've never actually observed one, but hypothetically, there's nothing necessarily forbidding it, but they will always have an even number. Back to the baryon for a sec. Again, same thing. You could have something with five quarks being a baryon, 7, 9, but it does always need to be odd, and we've only ever seen 3. They have an integer spin, making them bosons. Again, I don't want you to be stressing. You don't need to know that much of this, but it is kind of an interesting look at the bigger picture of matter at play here that all of your science life up until now has kind of ignored. So it's kind of cool. Okay, so examples of some baryons. Hey, our old friends, the proton and the neutron, very famous. Again, tomorrow we're going to talk a little bit more about what that means, that protons and neutrons are baryons. Examples of mesons, you've probably never heard of any of these. Pions, kaons, the psi, upsilon, and omega particles. But like I said, the other kind of big system we use for dividing them up is whether they are bosons or fermions, and then hadrons can be bosons or fermions. Okay, so like we've seen, we said baryons have a half integer spin, but they are also hadrons. So the half integer spin makes them fermions, but since they are composite particles made of quarks and they interact with a strong force, they are also hadrons, right? Mesons, composite particles made of a quark and an antiquark, and they interact with a strong force, so definitely they are hadrons, but they have a half integer spin, so they are fermions. See how they fit into both categories there? Mesons interact with a strong force, have a quark and antiquark, so they are composite particles, so again, definitely hadrons. However, they have an integer spin, which makes them a boson. What are bosons and fermions? It essentially boils down to which set of kind of quantum statistics they obey. Anything with a half integer spin, a fermion, cannot occupy what's called the same quantum state. Basically means they cannot occupy the exact same space at the exact same time, which such rules do not apply to bosons. You cannot have 2 electrons in the exact same space at the exact same time. No such rule applies to bosons, such as a photon. You can have 2 photons in the same place at the same time, no problem. Notice these are all the force mediating particles with the exception of the Higgs boson, which is not a force mediator, does something a little bit differently. So once again, just a reminder, you do not have to memorize these. I'm just showing you for the big picture scheme of things. And more importantly, to really drive home the idea that our models of matter were drastically changing as a result of our new discoveries. So there were far more subatomic particles than originally accounted for. If you want, you can flip to page 843 in your textbook and get just a small taste, very small taste. There's literally Wikipedia pages and pages and pages of the subatomic particles. There were so many that physicists started to call this the subatomic zoo. We thought we had a cute little subatomic picture with a proton, a neutron, and an electron, and it turned out we were in a whole zoo of subatomic particles that we didn't realize were there. Because, well, mostly they aren't there, but they do exist. They're real, so they need to be included in the model of matter. Now, something kind of troubled them. They noticed that there were only 6 known leptons, right? To this day, there's still only 6 known leptons. They're all incredibly small. In fact, some physicists even think leptons might have no size, no actual physical volume. They might be point particles. It's up for debate. And they had never been divided, right? We had never observed a lepton be split in half to this day. That's still never been occurred. So it really does seem like leptons are fundamental. But then they looked at hadrons, the other big category, right? They were relatively large, right? Hence the name thick. And there were hundreds of them. And so, what's kind of your feeling here, right? You start to think, well, if there's only 6 of these leptons, and we're saying that there's hundreds of hadrons, are these hadrons actually fundamental? Of course, we've spoiled that already, right? But you can kind of see their motivation. You said, well, maybe there's just a few particles that, in yes, different combinations give us hundreds of hadrons, but maybe we're missing something smaller here that is actually the unit that makes up hadrons. Maybe hadrons are not fundamental, but they are made up of something fundamental, and all of these different combinations of whatever those things are is giving us these hundreds of hadrons. It was really more of a hunch than anything. And we will answer that question in tomorrow's topic. If you're looking for practice with this stuff, you can try out the topic 3 practice assignment in the agenda or Google Classroom.